Okay, hi guys, welcome back. So let's continue from where we started. So we have our frame of reference. Then now I make it bigger, just uh, just because, and then like so. Okay, and now we have our ground. Okay, now we have our man, which holds a stone in his hands. Don't forget that we put a mask with some oxygen supply because there is no air. O2, O2 oxygen supply. Nice. Then we've got our stone with a mass M. So now, and he's happy. Now now he's happy to hold the stone and wants to do an experiment. So what does he need to do this experiment? So we know the origin, so we know that we can take measurements on X and Y, but we also know how to measure time. So let's put a clock. Okay, I don't. So let's put a wrist. Okay, whatever. This is a clock. Okay, and let's make it bigger here. So we've got hours and then seconds. Okay, good. The clock. So 12, 12, 1, 2, 3, 5, 6, whatever. Okay, we have a clock, we have a ruler, we have a mass, and we have a planet here, M. Now, we remember that the object is not moving because there are two forces acting on it, and they balance this. So the force, the reaction force of the hand, and the gravity pull of the planet. So so those two are the same at the moment. So the object is not moving. So what is Fg? Fg is what is called from Newton's law is r square. Okay, so there is a direction. In this case, the direction is y. It's a vector, so direction is y, which we call, by the way, we call it vy, just to stick with the notation of the previous slides. Okay, so now I don't remember what's the number of g, but g is the gravitational constant of Newton's law. R is the distance from the center of Earth, okay, to the object. So let's make it here with another color. This is R. This is big R. Suppose this is the center of Earth. So Earth is roundish. And then we got R squared. Okay, so now big M is the mass of Earth. We know that. And small m is the mass of the object. And the force is pulling downwards. Okay, so actually there should be a minus. Okay, because it's pulling down. Now, to make life easy, we call it F small g. Okay, where we bunch basically G, big M, and big R. We call it small g, which is whatever should be 9.82 meters second square. Okay, so we call it small g. So this is minus m small m g v y. Sorry, in green to remember that it's a vector, and those are other number v y. Okay, so this is the usual force of gravity that we experience on Earth. Basically, this is roughly constant. Shouldn't be constant because if you think about it, R can change wherever you are. If you're on top of the mountain, if you are deep down in the sea. Also, there are other considerations to take into account if you are inside the crust of Earth. But anyway, it doesn't matter. So for what we need at the moment is, I want to simplify the problem. So we use a simple g, the acceleration, gravity acceleration, whatever, the one that you're familiar with, which is 9.82 something meter square second. As you can see, meter over square second, because it's an acceleration, it's a derivative of second order of time, as we said before. So there is meter on top, which is space, and times twice in the bottom, because it's derivative of the second order. Nice. So we now we have everything. What we so we have a clock, we have a ruler, we have a force, and now we can let go our object, and let's see what happens. So as I said, we forget about the shape of the object. So the object is not a sphere, it's a point. Why I'm saying that? Because when you leave an object falling, if you do it properly or randomly, you impress some momentum, rotational momentum on the object. You can see that easily when you play ping pong, when you play tennis, or when you throw a ball in the air with a little bit of spin in baseball, for example, or you can try with a stone on a lake when you fling a stone on the surface of the lake. Depending on how you let it go, the motion will change quite dramatically, in fact. So we will forget about all of that stuff, not dealing with it. So we just drop it. So we literally let it go with as quick as we can, with let's say less momentum that we can. Now, when we let it go, what happens is that this force is no longer there, because our hand is no longer there, and there is only one force that is acting on the object, which is the force of gravity, which is mg. What does this mean? It means that the axis. So now we can see why. So now we can simplify the problem, because we see that F is equal to m times a. Now we have only one component, because we did let go the object easily, so we'll follow a straight line because we don't put any force in the x direction. So the force is only in y direction, so we can get rid of all the vectors because it's only one dimension. So we have got on this side, we've got minus gm, which is the force of gravity. On the other side, we have m times a y, the component of the acceleration in the y direction. Now, as we can see already, something very interesting happens. The mass cancel out. In fact, we know that when objects are falling, they fall at the same rate. This is what it means. So it doesn't matter how heavy an object is. If you don't consider friction, or if you not even consider the Archimedean force in the food, which is air, which is small but it's there, you can neglect those effects. All objects in vacuum fall at the same rate, which is exactly 9.82 meters per second, roughly, depending when you are on Earth. And this is the acceleration. But what do we want to know about this object? So we can find, for example, the time it takes to land on the ground. Why? Don't know, because for fun, we want to know how long does it take to reach the ground. So let's see how do we find the time in this equation. So we know that g is equal to the derivative of x twice. Okay, actually y, sorry, because we got it's a y dimension. And there is a minus. We can forget about the minus for the second by rotating the reference of red, but let's not fix it. We know that it's falling down, so we can remove the minus. It doesn't matter. So we know it's falling down. So we can adjust. So we just need to flip this axis or put the reference frame in a different way. It doesn't matter. So we are interested only in the time that it takes to land. Okay, so how do we take the time from this equation? So I think we need to first of all find the space, which is the easy thing that we can find, because we can integrate. So if we remember, when we have a derivative, we can integrate it to find the function inside. So we integrate g over time once between whatever clocks t0, which will be 0 because we put our clock start at 0, and t1, which is the thing that we need to find out. Let's see if I can get it right. And then we integrate this one, which is vy, so ay, but ay exactly. So let's see if I can do this correctly. So let's integrate once. So we've got vy, the one into t, and we integrate into t. Okay, which is the same thing as that. So okay, so technically we should do something a bit more formal than that, but for the sake of it, we just can cancel out this delta t over here because they are the same. So we do this. So we integrate. So we can see that the difference in so g is a constant in time. So we know that the integration of a constant is just sum of the time. So it's t1 minus t0, which is 0. So it's t1. And this is the difference of the velocity in t1 minus the velocity at time 0. But the velocity in time 0, we know what it is because it was 0, because it was we were holding it in our hand, and it was still. So that's 0, so we can cancel out. And we know that the velocity at time t is exactly g times t1, which is fine. Now we want to do a step further so we can get rid of this. We have our t, because we don't know what velocity we get at t1. We don't know that, right? Because we didn't measure the velocity. But we know we can measure the height of this because we know our tau we are. So we know y. We know y is 0, the initial distance from the ground. So let's try to do this trick once more. So we integrate gt over time once more between 0 and time 1. And then we integrate the velocity of y between 0 and t1. Okay. But sorry, the velocity is we know that there is the derivative of y over t in the t, because the velocity is the derivative of space over time. So we know that. So we do the trick again. Now you remember about the integration of t, of x or whatever. So, and this is t squared over 2. You can watch the video on the integral to make sure it's correct. We did it quite a few times, so we know that t1 square minus divided by 2, and in 0 is 0 because t is 0. And this is, we can cancel out this one again, and then we have, oh sorry, between 0 and y1, and we get y1 minus y0. And this is the distance, okay? This is exactly the distance that the object holds that we can measure because we know our height, and we call it delta y. And we call it delta y, which is a number that we can measure easily. Now it's done. As you can see, the time is there, and then we know the distance, and then we can derive t1 square is equal to dy times 2 divided by g, and then we take the square root of it. So I hope I didn't make mistakes along the way, but basically we can find the time by knowing the distance, the falling distance. So if we know, for example, the height of a roof, and we throw an object from the roof, shouldn't do it, but let's suppose it happens, you know how long does it take to fall in the condition where air is negligible. Okay, so this is a way just to see it. Yeah, so I will post if I find the reference for this formula somewhere I'm sure I can find it, but just to make sure that I don't mess it up, and maybe also this formula, which is the Newton gravitational law, which is quite, I mean, it's very important. I mean, it was a huge achievement. So let's, I think I will stop here. I hope you enjoyed it, and more to follow. I will also post a summary of what we said today in some better calligraphy to make sure that we got something out of it. Okay, hope you like it. See you next time. Enjoy.